Okay, think about the device you're using right now. Your phone, your laptop, whatever it is, it's being powered by a little box of chemicals. But have you ever really stopped to wonder what's actually going on inside that battery? Well, today we're going to peel back the cover and look at the secret, invisible dance of chemistry that creates electricity.
So that's our big question for today. How does it happen? How do you get from a bunch of chemicals to the power that runs your entire life? It feels like magic, right? But the answer is pure science. And that science is called electrochemistry. At its heart, it's really simple. It's all about the relationship between chemical energy and electrical energy, how one can turn into the other and then back again. This is the bedrock science behind every single battery you have ever used.
Now, this whole energy relationship, it's a two-way street. It's not a one-way transaction. You can either get electricity from a chemical reaction, or you can use electricity to make a chemical reaction happen. And these reactions, they happen inside things called electrochemical cells. And they really come in two main flavors. On one side, you've got the galvanic cell. That's your classic battery, the kind that just spontaneously makes power. On the other side is the electrolytic cell. That's the one that needs a power source to force a reaction happen. Think about when you're recharging your phone.
So let's just break that down real quick. Our hero for today, the galvanic cell, the battery, takes a chemical reaction that wants to happen all on its own, a spontaneous reaction, and it turns that chemical energy into electricity. You'll notice the anode is negative and the cathode is positive. Now the electrolytic cell, it does the exact opposite. It uses electricity to push a reaction that wouldn't normally happen. So since we want to know how a battery makes power, we're going to focus completely on the galvanic cell.
All right, let's get our hands dirty and dive in. To really get how a battery makes electricity, we're going to build one of the classics right from scratch, the Daniell cell. And here it is. Now I know, it might look a little complicated, but the idea is actually super simple. You've got two beakers. In one, there's a strip of zinc metal in a zinc solution. In the other, a strip of copper in a copper solution. These metal strips are called electrodes, and we connect them with a wire. But here's the unsung hero of the whole setup. This U-shaped tube called a salt bridge. It connects the two solutions and lets ions flow back and forth. Without it, charge would build up and the whole reaction would just stop cold.
Okay, this is where the magic really happens. Two things are going on at the exact same time. Over at the zinc electrode, you have something called oxidation. And a great way to remember this is the little saying, oil rig. Oxidation is loss of electrons. The zinc atoms are literally losing electrons. At the same time, over at the copper electrode, you have reduction happening. Reduction is gain of electrons. The copper ions floating in the solution are gaining them. Let's look at the actual chemistry. See that top line? That's a zinc atom giving away 2 electrons. And the second line? That's a copper ion grabbing those 2 electrons. So where do those electrons go? They can't just teleport. They travel from the zinc up through that wire we connected and over to the copper. And that flow of electrons through the wire, that right there is electricity. You know, chemists had this really cool shorthand for describing this whole setup. It's called cell notation. Yeah, it looks like a secret code, but it's really just a recipe. It tells you everything you need to know. The zinc anode is on the left, the copper cathode is on the right, and see that double line in the middle? That's our salt bridge, connecting the two halves. Pretty neat, right?
So we have a flow of electrons. We have electricity. But what determines the push behind them? What we call voltage. Well, the most amazing part is that we can actually predict the voltage of this battery with incredible accuracy before we even build it.
The key to this is a concept called electrode potential. The best way to think about it is like a material's personality. It's a measure of its natural tendency. How much it either wants to give up its electrons, like our zinc, or how badly it wants to grab new electrons, like our copper. The voltage is just the difference between those two desires.
But wait, how do you measure a desire? To measure anything, you have to have a starting point, a baseline, right? Like if you want to measure how high a mountain is, you need a 0 point. You use sea level. Well, in electrochemistry, we need the exact same thing.
And this is our chemical sea level. It's called the standard hydrogen electrode, or SHE for short. It's brilliant. By international agreement, scientists all over the world just decided that the electrode potential of this very specific setup is exactly 0 volts. It is the universal benchmark that everything else is measured against. So now that we have our 0 point established, we can start measuring the potential of every other element against it. And when we do that, we can create this amazing master ranking. kind of like a chemical league table. It's the ultimate cheat sheet for building batteries.
And this master ranking has a name, the Electrochemical Series. It's just a big list of elements, all arranged by their potential, telling us exactly how much they want to gain electrons compared to our friend, hydrogen. It's an unbelievably powerful tool.
And here's what it looks like. Let's find our players on the field. You can see hydrogen, right there in the middle, our 0 point. Now let's find our two metals. Okay, here's copper, with a positive potential of plus 0.34 volts. That means it wants to gain electrons more than hydrogen does. And way up here, here's zinc, with a negative potential of minus 0.76 volts. That means it wants to gain electrons much, much less than hydrogen. In fact, it would much rather just lose them.
So, here's the really cool part. The total voltage of our battery is simply the difference between the two. We just take the cathode's potential, that's copper, at plus 0.34 volts, and we subtract the anode's potential, zinc, at negative 0.76 volts. So, plus 0.34 minus a negative 0.76 gives us exactly 1.10 volts. The electrochemical series told us the exact voltage of our battery before we even put the wires together. How cool is that?
And that's really it. That's the secret life of a battery. It's just a controlled chemical reaction driven by the different natural tendencies of materials to play hot potato with electrons. It really makes you wonder, doesn't it? If this basic knowledge and a simple table let us perfectly predict a battery made from zinc and copper, what other powerful, incredible new combinations are just sitting there on that table, waiting for someone to design them and power our future?